doing example 2 from section 6.2. This is kind of a longer word problem, a little bit more difficult than the last one, but it has an actual practical application here. So I've got the picture drawn as you see on the worksheet there. So it says a company wishes to run a utility cable from point A here to the island out here. Okay, and what they want to do is minimize the cost. So the reason that we can't just go directly from here to here, it says it's more expensive to put the cable underwater than it is to put it on land. So it seems like we can run it partly on the land, and then at some point we break off and then go underwater for the rest of the way. And what we're wanting to do here is actually minimize the cost. That's the goal. Minimize the cost of the cable. Okay, so in order to do this, we have to figure out a formula for the cost, for the total cost, based on what I have drawn here. So in fact, I've actually added a couple of other things to the drawing that you see on your paper here. In order to actually solve this problem, we're going to have to label a couple of things. So what I did here was I said, all right, let's let x here be the distance from point C to the point that we want to sort of break off and run the rest of the cable underwater. Okay, so that's unknown. I'm going to call it x. Now if I call that x, then what's the remaining part from that point to A? Well, it's 9 minus x, since the entire distance is 9. Okay, and so what we want to do next is we want to determine what constraint we have. Well, in this case, the constraint comes from the shape of this piece of the drawing right here. That's a right triangle. So it follows the Pythagorean theorem. And so what we want to do, the constraint that we have, will be based on that part of the drawing. It's a right triangle, so we can say x squared plus 6 squared is equal to, and I labeled this side here z. You don't really have to call it that, you can call it whatever you want. But that's the relationship that we have between the two quantities x and z. So what I want to do is I want to put everything in terms of x, because that's going to help us to figure out what the cost function actually is. So to do this, in fact, actually, let's go ahead and, well, let's solve this thing for z real quick. If I solve for z, all I have to do is take the square root of both sides. So z is going to be the square root of x squared plus 36. Okay. And then we can construct the cost function. Now c, the total cost, is going to be, well, to figure out how much money that we're going to have to spend, we have to know how much it is per mile, and then how many miles we're actually going to run. So to get from here to here, how far is that? That's 9 minus x miles. So we're going to run it that many miles, and then we want to multiply that by the cost per mile. It says that the cost per mile, if we're on land, is $400. So this is the distance that we're going, and this is the cost per unit distance. Okay, and then, so that's the part on, this is the on land part, and then we've also got the on water part. Well, the water part is going to be this distance here, which I've called z, but z is actually that. So I'm going to write it as the square root of x squared plus 36. And then I have to, so that's the distance that we're going to go, and then I have to multiply that by the cost per mile for underwater, which it says is 500. So this is the total cost right here for the on land part. This is the total cost for the water part. So if we, in fact, we can now even call this c as a function of x, c of x. It's not c times x, that's c of x. And then let's go ahead and simplify this a little bit. If we write this, if we distribute that 400, we're going to get 3600 minus 400x. And let's just put the 500 in front on the other one. So 500. And then let's write this as x squared plus 36 to the 1/2 power. Okay, so that is the cost function. What this function is going to tell us then is if I plug in any value for x, it will tell me what the total cost is for laying that amount, or laying that cable, depending on what x happens to be. And remember what x is in my drawing here. X is the distance from this C point. So if I make x really small, then it will tell me a cost. If I make x really big, it will tell me a cost. But we also need to think about, well, what values of x can we actually have for this thing? In other words, what is the domain of our x function here, of our c function? Well, the domain, what is the smallest that C can possibly be? Well, I can make C be 0, and that would mean that I was basically going to run the entire thing on land until I reach that point, and then I'm just going to go straight out in the water. Okay, so that's, if C is 0, that's the smallest value I can have. What's the largest value that I can have for C? Well, the largest value would be, well, if I just started here and just put the entire thing underwater and went straight up to B. Okay, so that would be, how big can C be in that case? It's 9, right? So 9 is the largest value that C can, that I can plug into this function C of x. Okay, so when I have to consider that at the end here, because according to our list of things we want to check, we do want to plug in the endpoints just to see what might happen. So anyway, the next step is to find the critical numbers for this, and that requires the derivative. So we'll take the derivative of this thing. The 3600 is going to go away, so I'll get minus 400. If I bring the 1/2 in front there, I'm going to get 250, and then I'll get x squared plus 36. I'll have to lower that power by 1, so I'll get minus 1/2, and then I've got a chain rule, so that's going to be multiplied by 2x. Okay, so let's rewrite this function a little bit. I'm going to have to write a lot on here, so let's try to squeeze this in. We'll get minus 400. Let me just sort of separate that off of there. Minus 400 plus 250. In fact, actually, let's go ahead and multiply the 250 and the 2 here. That's 500x, so we'll have a 500x. And then in the denominator, since that's a negative exponent, we can move it down. So that's x squared plus 36 to the positive 1/2, which is the same thing as the square root of x squared plus 36. Okay, so there's our cost, the derivative of the cost function. To find the critical numbers, we want to set this to 0. So to solve that, I'm going to move the 400 over to the other side. So I'm going to get 500x over square root x squared plus 36 is equal to 400. Okay, we can cross multiply on this one, or just multiply both sides by that root in the denominator. That's going to get us 500x is equal to 400 times the square root of x squared plus 36. Okay, so remember, what we're doing at this point is solving for critical numbers. If I divide both sides of this thing by 100, in fact, actually, let's go ahead and divide both sides by, just 100. So we'll get 5x is equal to 4 times the square root of x squared plus 36. Now I need to solve this for x. The best way, I think, to do that is we have to get rid of this radical. So I'm going to square both sides of this. Square both sides, that'll get rid of the radical. So that's going to give me 25x squared. Now I have to square the 4 as well, so that's going to give me 16. And then squaring the square root takes away the radical. So I'm left with x squared plus 36. I'm getting a little close here, running out of room, but I think we'll be able to fit everything. So next, we'll divide both sides by, or actually no, in this case, let's distribute that 16. We'll get 25x squared is equal to 16x squared plus 16 times 36. I'm not thinking, can't do that in my head right now. 36 times 16 is 576. So these are like terms. I can subtract. It's going to give me 9x squared is equal to 576. Divide both sides by 9. I get 64. So x squared equals 64. And we know what that is. X is equal to 8. Okay? So that's the critical number. And remember what x stood for. X is the distance away from this C point here. So really what we have then is 3 possibilities. Do I just go all the way here? In other words, if x is 0, so just go on land until I reach here and then do the rest in the water. Do I just put it all underwater? Or do I use this one where I go out 8 miles, which would basically mean I'm just going to go 1 mile away from there and then the rest in the water. So which of those 3 is the best option? The way to do that is to figure out what is C, what happens when I plug C, or 0 and 9 and 8 into the cost function, see which one gives us the largest, or actually in this case the smallest cost that we're trying to minimize. So C of 0, if I come back up here to my original function and plug in 0 here, let's see what happens. I'm going to get, that will be gone. If I plug in 0 here, that's 36, the square root of 36 is 6, so I'll have 500 times 6. 500 times 6, that's what, 3,000, so 3,600 minus 3,000, that'll be $600. If I plug in the other endpoint 9, see what happens if I do that. Notice if I plug in 9, oops, I think I plugged, no, I'm sorry, I plugged this in the wrong thing. Disregard what I just said about that. I'm supposed to plug it into the original function, not the derivative. So let me redo that. Sorry about that. So C of 0 would be what I get when I plug in into this original function here. So if I plug in 0 here, 9 times 400, in fact, actually, let me just use my calculator to plug this in. F of 0, we get 6,600. Sorry about that. I plugged it into the wrong thing. If I plug in the other endpoint, 9, in other words, that would be if I just go entirely in the water. Let's see what we get there. I get about 5,000, so this is C of 9, $5,408. So it's less if I just run underwater the entire time. This would be on land the entire time. And finally, what happens when I plug in 8? That was the critical number that we got, and I get 5,400 for that one. So C of 8, 5,400. Well, clearly, that's the smallest cost right there. So if we run it 1 mile away from here, remember C is 8 would mean, I said that X was this value here, the distance away from that C point. So 8 miles away from there would be only 1 mile away from A. If I run it 1 mile on land and then the rest underwater, you see, that's going to give us the smallest possible cost. Okay? So that's what we're after. That's the answer to this particular question.